Hi, my name is Manmeet, and I'll be going over the survey on face data augmentation. The original paper is written by Wang et al., and it came out in the April of 2019. So the main motivation behind, choosing this paper was that face that data augmentation in general is a important problem because, you know, face is one of the most studied um, aspects of day-to-day life, and the various techniques that I would understand here could be applied in another domain. So the main idea behind augmenting face data is to overcome the limitation of existing data, represent uncaptured distributions, how a person might look on their day-to-day life, would they change the hairstyle, makeup, and other things like that, and generate faces without self-occlusion. So, people tend to generally kind of move around freely, and, sometimes things get in the way of, um, an instance of a camera capturing somebody's face. So how do you kind of get around that and, still get to a higher degree of certainty if that it is the same person that you're concerned with? And lastly, to generate faces with more intra-class variation. So, same person has a higher category of, um, data associated to their name. So there are basically there are three different types of transformations. There's the generic, component, and attribute. The generic is geometric, photometric. These are basically, shifting, twisting, and photometric is, playing with the RGB channels and, gamma filters, the contrast ratios, and things like that. Component is, things that kind of people have on their face on day to day, like hairstyle, makeup, accessories, and attributes are, things associated with someone's being, which is their pose, expression, and their age. Um, so getting into the generic transformations, these are basically flipping orientation, cropping and padding, um, photometric, ultra RGB channels, edge enhancement, blurring, and as you can see here in the picture, these are some of the various ones that you know you might see because of, like, outside conditions changing on a day to day, or somebody being outdoors at night. So it's kind of important to capture that entire distribution to get a good set of training data. And the next is the component transformation. This is the hairstyle transfer, makeup transfer, accessory transfer. So hairstyle transfer is, having an input image and taking somebody's hair that um, you know, potentially looks like them or not. And, GANs have been used in this area quite frequently, um, because of their architecture, where the, um, generator tries to fool the discriminator. So all of these would be generated by the generator. And then this is how a person might potentially look at any given, period of their lifetime. And if the GANs can do a good enough job in coming up with this data, then, um, you're taking a successful step towards augmenting your initial data and having a better, facial recognition at the end of the day. Um, for makeup transfer, there's another GAN called the Beauty GAN, which basically does a context-aware, um, style transfer. So it kind of understands, you know, that your cheeks generally have more makeup, and and there's more makeup around your eyes generally if you're if you're a female, and so that's the speciality of um, beauty GAN there. And then accessory transfer is you know this is mostly concerned with eyeglasses because those are some of the things that people tend to take on and uh, you know and take off most of the time. So moving right along, pose transformations are based on you know so there's a traditional techniques which are PCA and 2D model shapes, and then so in these techniques you basically try to boil down the shape of a person's face into some some fundamental latent variables, and then try to recast it in another side of their face. And then there are the other GAN-based techniques where UV GAN is used to complete the UV map and recover self-occluded regions. Um, So, and then the next GAN, the CAP-G GAN, is it does a flexible face rotation of arbitrary head poses from a single image in 2D space. So this is more of kind of the same. And then there are various other GANs for basically recognizing what the basic features of your face are from a geometric perspective, as well as from a color and contrast perspective, and then they try to reconstruct your face in a different orientation. um and then for expression, there are basically four primary GAN categories, and these can be based on reference, target, and images, or variable generation of expression codes. The third is the continuous action unit coefficients. These are basically kind of like flow graphs. Like if you're turning, like left or right, what are basically the different um, what are basically the different images you can capture in that instance. And then the fourth category is basically GANs that preserve identity um, in doing expression transfer. So if somebody smiles, like how realistic is it compared to how they would actually look when they smiled? And then the last one is age, and there was a famous app that came out recently. I think it was like last year, where you could see the older version of yourself potentially. But it basically, you know, this technique kind of preserve your basic facial geometry, and then casts, the delta between all the other training data that it's learned from how somebody looked when they were young versus how they look when they're older. Um, So getting right along. So what we talked about up until now were the transformation types, and then now we get into the methods, specifically like what methods get deployed to do all the various different types of transformations. So like I've been saying here and there, right? So there are the basic image, there's basic image processing, which is the traditional, kind of like taking Photoshop and doing the best you can with that. Um, the other one is the model-based transformation. So you fit existing model to an input image. So realism enhancement, the generative-based transformation, augmented reality, and augmentation. So I'll mostly be focusing on the generative-based transformation, just because those seem the most interesting at this point in time. And then here, have a general architecture of the I believe this is the data augmentation GAN, the DA GAN. Um, and it follows the typical encoder and discriminator, encoder decoder and discriminator architecture. So um, you provide a true image to the encoder. It tries to learn some kind of you know latent representation, and the decoder uh, puts that back together, and then you basically go over here to the discriminator to see if any other image that it generated, how it compared to the true image that came from the original base data class pool. um, and so you basically do the game theory here, and then these two guys, they play their game until the discriminator can no longer tell apart what's real and what's generated. um, the next part is, so getting into generative transformations. um, so there's the autoregressive generative models, variation autoencoders, GANs, flow-based generative models. So um, autoregressive gen models, basically they model the joint distribution by decomposing the, the instance into a product of conditional individual variables. Um, and then here is what basically GANs do. They generate a they generate an image, and then you basically say, hey, how much does this differ from a real instance, which is what a discriminator tries to tell apart, and then you call that your loss, and then you minimize, how well the discriminator is able to tell these two apart. And then the next is, so this is the general architecture of the cycle GAN, and this learns the mapping between two high dimensional data domains. So traditionally, most GANs, they learn mapping between a low dimensional and a high dimensional data domain. So, basically, GAN tries to figure out, say how a person looks when they're younger versus how they look older. So it kind of does that delta between a lower dimensional domain and higher dimensional domain. So what CycleGAN does is it can basically, style transfer from, say, a zebra to a horse, which is the equivalent of saying, how would, like, my friend who's like, how would my friend look when he's, say, 65, and how I would look, and then the CycleGAN would be able to transfer his face onto mine, both of us being the same age, and the CycleGAN learning from some independent data that is not related to either of us. So that's basically the speciality of CycleGAN, and it's the cycle loop, this cross pollination of the both of the generators here that kind of help them um, be able to generate more realistic images, as well as keep a grasp on, like, what they're learning fundamentally. So lastly, we get into the evaluation metrics. The most of the evaluation metrics are basically based on qualitative and quantitative. So qualitative are basically, you ask a bunch of people how your generation looks. Quantitative is distance measurements. You do L2 and L2 norm for color and space, and then accuracy and error rate, inception score. So relative entropy between two distributions, like Kale divergence or something of that sort. And then there's this Frechet inception distance, which is between two multivariate Gaussian distribution of real and generated. You try to figure out how close are they and what are the differences. So lastly, the challenges and opportunities are basically identity preservation, because a lot of times the generated data tends to lose the fundamental thing that kind of makes a person who they are on a day-to-day. um, you know so that definitely needs more work, according to the survey paper. The others are disentangled representation, unsupervised data augmentation, and in general, improvement of GANs. GANs have come a long way in the last 3 years, but you know there's still a long way to go. And that is it for my presentation. Thank you for listening. Bye.